Hi, I'm Ed Sperling. I'm the Editor-in-Chief of Semiconductor Engineering. I'm over at NXP with Wouter, Sijm, who's going to talk today about sensors. Why are sensors getting so popular these days, and what do we need to know about them?
Yeah, that's a very good question. So sensors have been around for decades. So we've been using them in cars, in airplanes, in thermostats, in many different kind of products. But over the last few years, there's been a huge increase in number of sensors which are being used. So this trend mainly started about 7 to 8 years ago with the introduction of the first generation of smartphones. So these smartphones already had a lot of sensors integrated into them for that time. And users quickly got adapted to their features. So you can use them, for example, for user input or for games. And with each generation of new smartphones, the number of sensors actually kept increasing. So a smartphone nowadays easily has up to 10 or even more sensors. So you can use these sensors to determine the context of the user, for example. So you can determine whether the user is in a quiet office or on the bike or in the car, and you can do all kinds of things based upon that. You can also use motion data, for example, for tracking the location of a device. So you can see where to it's moving. You can use it, for example, for indoor navigation.
These are accelerometers, gyroscopic type of sensors?
Yeah, exactly. Yeah, for motion you're talking about accelerometers, gyroscope, magnetometers. But there are many other different kind of sensors. For example, proximity sensors, which are used to determine whether you have your phone, for example, in your pocket or close to your face. You can measure barometric pressure. Even audio is used nowadays to determine the context of the user.
So as we get more and more sensors in these devices, are they starting to compete for both bandwidth, for memory, for the power that's there?
Yeah, that's definitely the case. So what we've been seeing lately is especially a focus on power. So you can imagine that if you have all these sensors and you've got them running a lot of the time, for example, if you want to do step counting on the phone all day long, you would need to enable these sensors all day long to enable step counting. So if you would have that always on sensors, it will drain your battery really fast if you do not do it in a proper way.
So how do you manage the power? What's the most effective way of dealing with this?
So with the first few generations of smartphones, the application processor, so the main processor in the phone, would handle these sensors. So it would continuously sample all these sensors. And because of the nature of application processors, they're very powerful regarding performance, but they're not really power efficient. And also the wake-up time, if you want to enter a low power mode in these application processors, is pretty long. So this means that if you would do, for example, step counting on the application processor, it will drain your battery pretty fast. So the solution to this problem is to add a low power microcontroller to the device, which acts like some kind of a co-processor. So we usually call this a sensor hub because it interfaces with the sensors. This is a good solution to keep the power as low as possible, because you can not only sample the sensors using this processor, but you can also actually process the data that it receives. It can do the step counting, it can do calibration of the sensors, it can perform what's called sensor fusion. So it combines the data of all these sensors, and it only has to wake up the application processor when the user asks for the data. So it doesn't have to be running all the time when you have your phone in your pocket, but you still want to do step counting.
Why don't you draw this out for us and show us where we run into problems?
Let's say we do step counting. So for step counting, we maybe need to sample accelerometer and gyroscope at a 10 Hz rate. So that means that every 100 milliseconds we have to sample these sensors. Now a typical application processor has a wake-up time of 500 milliseconds. So that means it has to stay awake all the time to be able to sensor these samples at this specific rate. If we draw the power consumption, it means we basically got a constant power consumption, because the AP has to stay awake to do this processing. And typically for an application processor, that can easily be 75 milliwatts. So if you would calculate the energy consumed by only doing step counting, it will be a lot of energy. So the solution to this problem is to use the low power sensor hub to actually offload the step counting to and only wake up the application processor when needed. So in that case, the graph will look very different. So the sensor hub typical power consumption is a lot lower. So instead of 75 milliwatts, it can be as low as 1 or 2 milliwatts. So really at the very bottom of the same graph. So let's say 2 milliwatts. And only when the user wants to know the current step count, it has to wake up the AP for a very short moment. It can go back to sleep as soon as the user is done. And then again, step counting resumed at very low power consumption. So of course the energy consumed in this case is a lot lower than when using the application processor to do the same.
Not all sensors have to respond at exactly the same time. Your backup camera, for example, on your car has to come on immediately, but say the sensor in your heated seat will be a lot slower. How do you manage, particularly with sensor fusion, how do you manage that kind of differentiated response time?
Yes, so what you're talking about here is mainly different sample rates, if I understand correctly. So indeed, the rear view camera needs to be updated. Probably 20 to 30 times per second. Well, you need to sample the temperature of your seat not as often because it doesn't change that fast. So this is very specific to the application. Usually there is some central entity which controls all these sensors. And depending on the application, the sample rate for these sensors are configured differently. So some sensors have the ability to set a rate. So instead of having to manually pull each time the sensor will just generate an interrupt to the main processor, and main processor will issue a read of that sensor. But in other cases you may want to manually set the sample time by using a timer.
And that happens on a much more concentrated level on, say, a smartphone, for example, where you're holding the phone up to your face and it's not picking up it understands that you don't need to see the screen then, and it powers the screen down and then comes back very quickly, versus something else in the phone which may not need to be updated as quickly too, right?
Yeah, that's definitely true. So when you're talking about sample rates in a mobile phone, they're typically quite fast. So the 10 Hz example I gave earlier is pretty slow. Often you will see even 50 up to 100 Hz of sample rates. And again, this is really dependent on the type of sensor. So some sensors are slower. For example, a magnetometer which would sample the magnetic field of the Earth typically is slower than, for example, a gyroscope, which needs to measure rotation really fast.
So if you're dealing with sensor fusion, for example, you may have one sensor which does multiple things, and each one may have a different response time. How do you work with something like that? It may have a different power envelope for each different process.
Yeah, that's right. So if we would look at a mobile phone, each application can request certain sensor data. So one application may request just the accelerometer at 10 Hz, but another application may request the 9-axis sensor fusion, so combined with gyroscope and magnetometer, at a much faster rate. So when doing sensor fusion, you also must really take care of synchronizing all these different applications and make sure that each application receives the rate that it requested.
How much of that is done in hardware, how much is done in software, and how much is a combination of both?
It's a little bit of a combination of both, actually. So each sensor can usually be configured to take a sample at a specific interval rate. So if you have a simple use case with just a single application requesting the data of this single sensor, then it's easy. But then you can basically do it all by hardware. But if you have multiple applications requesting multiple rates, then you really need to do some abstraction software to handle that.
And the architecture, how does that affect how the sensors respond in terms of time and both time and power? The architecture of the chip, the architecture of the system, throughput, things like that.
Yeah, that has a big influence. There used to be a case where just the application processor of the phone would take care of all the sensor sampling and the processing. But nowadays what we often see is that a special dedicated low power sensor is being used to do this in order to keep the power as low as possible.
You think about a baby monitor, for example, where now you don't just have sound, you also have potentially temperature sensors, you have motion sensors in there that you didn't have before. If you're an engineer designing one of these chips, what do you need to think about?
Yeah, that's a good question. It will become quite complicated. So you're talking about temperature. We're talking about sound. And if I remember correctly, you're talking about motion. So these are the main external events that you need to deal with. So you will need different kind of sensors for these. So it could be that the temperature sensor is a simple I2C temperature sensor. So you will need an I2C bus on your system to be able to listen to this temperature sensor, to sample it. The motion, maybe it's a different kind of interface that you need. It might be, for example, an SPI interface, which can handle higher bandwidth of the data. So that's a challenge to have multiple buses on the system. And probably sound is even more interesting. If you want to do, so let's assume this is a battery operated device, right? So you probably want to do the sound continuously, but you need to be very careful at the power consumption. So you probably want to use a digital mic. So digital mics are becoming more and more popular because of the size and the power consumption, and because they're pretty easy to interface with.
But they also tend to use a lot more power than some of the analog stuff, right?
The mic itself maybe does, but you can save it because you do not need an analog circuitry to interface with the microphone.
So as you're putting these together, what do you need to think about?
Probably the biggest challenge again is power consumption. So regarding the sound, you probably want something which is called VAD, which is voice activity detection. Which basically means that you can stay in a low power mode, the main processor is still asleep, while still listening to the ambient sound. And only when you hear something that is likely of interest, you will wake up the main processor and you will do a high quality listening to see what's really going on and to detect that.
So can you draw this out for us in terms of a diagram where the sensor actually fits into a device and how it looks?
Yeah, of course. So centrally you will have a processing unit, so like a low power microcontroller. On the outside you will have different kind of inputs. So for example over here we've got a temperature sensor. Then another sensor that we want to interface with would be, for example, an accelerometer to detect motion. And also we've got sound that we want to listen to. So we use a digital microphone to do that. So the temperature sensor could be controlled over I2C. So we have a single I2C bus which connects to the temperature sensor to sample it. So the accelerometer, depending on the type, it might go to the same I2C bus, or it might actually have a different kind of bus, and it needs a separate connection. For example, if you choose one with an SPI interface.
And the advantage there would be better direct connection, but potentially just more circuitry, right?
Yeah, that's true. Yeah. So for the sound, for digital microphone, you typically need two signals. One is a clock. So this will determine basically the quality of the audio. And what goes back is the digital data. So the digital data which comes back needs to be processed. And because it's a digital mic, you need to do quite some processing. So you need to convert it from what is called PDM, pulse density modulation, to PCM, pulse code modulation. So that's the first step that you need to do in the microcontroller. So some microcontrollers offer the feature to do this by a separate hardware block, so that you don't have to do it using the core of the microcontroller.
So one of the things about the IoT is that engineers are finding that they can't just use a lot of the same components that they've been using in the past. What are you seeing? Why is that happening?
Yeah, I totally agree. So every device, every solution that you create must be tailored specifically to the application that you're developing. It's really hard to take something, a similar product, and reuse it. You may do it, it may go alright, but it will definitely not be the most optimized application. So you will probably need to cut down the requirements if you want to reuse a lot of stuff.
Wouter, Sijm, thank you very much for a great explanation.
Thank you for having me.